Okay, welcome everybody to the afternoon session. Now we have Jørgen Andersen with the Automorphism Equivariant Hitchin index.
So thank you very much. And thank you for asking me to come here and give a talk at this wonderful occasion, Oscar, at your 60 Epsilon's birthday. So I have a proof that I certainly know Oscar before Andrew does, because Andrew thinks that we were office mates to begin with. But this is not the case, because I think that at the time Oxford was taking a lot of graduate students, and so Nigel had 3 students that were sent in exile in Dartington House. And actually we arrived over there more or less at the same time. And there was a little funny thing happening in the beginning of when we were in this office. So none of us sort of met each other right away, but every time we went into the office, something had moved around the tables, and there was a little dispute about who got the best table, who got the second best table, and who got the third best table. I am not going to tell you how that ended, but I can just tell you I gained a friend for life. So yeah, the Automorphism Equivariant Hitchin index. So let me try to, as quickly as I can, get to what I mean by that. So I'm going to take C to be a Riemann surface. I'm going to take F to be an automorphism of this Riemann surface. And I'm going to assume that that is of prime order P, and P is an odd prime. So these few, I mean, that it's finite order is absolutely crucial for what I'm going to do. P odd prime is actually not really, but it makes it much nicer and simpler to present the results in this case here. So, excuse me? Yeah, they're coming now. Thank you. So the genius of G is going to be bigger than or equal to 2. Yeah. No, I agree with that. But I may not have taken an element of prime order in the group, right? But I will. Okay, and so I'm going to define the CF to be C divided by the group action. And so I have a projection from C to CF. And inside here, I have the special orbifold points. So in this case here, the generic orbits will be of size P, but some orbits, in this case P is odd prime, might be fixed points. So there's only those 2 possibilities, full orbit or fixed points. So delta is the fixed points. I can either think of them in C or I can think of them in the quotient. Okay. So now I'm going to take lambda, an odd degree line bundle on CF. And I'm going to, let me call that prime. And then I'm going to let lambda be the pullback of this line bundle to the cover, or to this C here. So that's again an odd degree line bundle under these assumptions here. And so what I now want to do is I want to look at the Higgs bundle moduli space. So I'm going to look at the Higgs bundle moduli space. So rank 2 and determinant isomorphic to lambda. So I'm in the co-prime case, so this is a smooth space in this case here. And so, of course, what I get this way is I get an action of F, and I'm going to, in order to not to have star upon star upon star, all the different actions of F will still be called F. Okay. So I have, of course, an action of F on M, and I can look at the determinant line bundle over M, this guy. And so I can look at H0 of this line bundle, and I can take kth powers of it, And of course, so, you know, there's a way to actually lift this automorphism here to this line bundle here. And so I actually get an action of F also acting on this space here, like that. So this space here is, of course, infinite dimensional. All right. Now, sorry. I also get an action on this, where Q is you know, any non-negative integer. Okay, so what I want to do now is I want to look at the, you know, C star action, so the T action on M. Of course, it has this famous C star action, which Nigel introduced on this space here. And so, of course, the T star action can also be explicitly lifted to the bundle. And it commutes, can be all done in such a way that it commutes exactly with the lift of the automorphism action on the line bundle. And so because of that, I can get a decomposition. And so I can look at the isotypical components of each of the cohomology groups like this. So I'm going to write that as a big direct sum. And the way that I normalize things is that M will be equal to 0 to infinity. And then I have the Q mth isotypical component of the space here. It just means that when the C star action acts on this space here, it does so by M times the standard action of C star on C. Now, all of these pieces are finite dimensional. So therefore, I can make the following definition. So I can define the equivariant Hitchin index like the following. So I take chi, so it depends on k, of course, is the power of the line bundle. It depends on t. And so it's simply just the following gadget. I sum M equals 0 to infinity. I sum over Q. I take -1 to the Q. And then I take the trace of F acting on the M's isotypical component like this. And then I take a generating series that takes T to the M this way. So that's the equivariant Hitchin index. Okay. And so the theorem, so what I failed to say, but which will be completely obvious now, from what I write now, is the following theorem. And so this theorem is due to Thomas Hausel and Mistegard and myself, which says that this guy here, so maybe before I state this, let me see where I can introduce this. So there's actually a gadget that I can define here. This is going to be XF. And this is just take the Riemann surface, cross with the interval from 0 to 1, and divide by an equivalence relation. That equivalence relation says that x, 0 is equivalent to f of x, 1. So I just take this 3-manifold with boundary, and I glue the two ends together with f, so that's a mapping torus. It's a closed oriented 3-manifold. And so this theorem here says that this gadget here only depends on a ISF of XF. So ISF stands for the Seifert invariance of this 3-manifold. And so, of course, we don't sort of abstractly just prove this. What we do is we give a formula which only involves the Seifert invariance. So now I'll give you what the Seifert invariants are. So let's have a look here. Yeah, maybe I should just address the following first, namely that so there's a second sort of theorem that says that if there are no fixed points. Okay, so if there are no fixed points at all, this is a perfect p-fold cover. So that case is special, and what happens in that case is the following: that if you look at this character here for f, then this here turns out to be the Velinde formula for, so that depends on the genus and the level, and then this t parameter here. So it's the Velinde formula for Higgs bundles. So g of the quotient, and then k, and then t to the p, where this is the Velinde formula, which I've done together with Sergey, Glukov, and Dupay. So that's a very special case. So it turns out that simply just to give the Velinde formula of the quotient surface, but shifted by this t to the p. Okay. So from now on, I will assume that there are fixed points. Okay, because now we dealt with, I mean, this here clearly establishes that this is the theorem, because this is a formula that tells you it only depends on genus of the base and then the two variables. So that's clear. So that's a special case. Okay, but now let's look at the Seifert invariance of this guy. So suppose that I take a y, which is a fixed point. Well, then, so at this fixed point here, f will tangentially rotate by some amount, and this will be a pth amount of a full rotation somehow, but it could be, you know, just not exactly a pth, but some. So let me say it the following way. So there is a q twiddled y, which is in between 0 and p, with the property that if I take the trace, so this is just a coordinate invariant way of writing this. So if I take the trace of dfx, then this here can be written as e, sorry, right down here, e to the 2 pi I, q twiddle y divided by p, where q twiddle y and p are co-prime. Right, so it will be some rotation of this form here. It's p's powers identity, so that fits exactly. And so now I'm going to introduce another guy, qy, which is the inverse of qy twiddle modulo p. Okay, and so qy is also in this interval here. And now the Seifert invariance of this xf is, so in general, they are like this. There is an integer b, there's another integer g, and then there are co-prime integers alpha 1 up to, sorry, beta 1 up to alpha n, beta n. Okay, and so in this case here, in this case here, it is minus p sum over 1 over qy, y in delta. And so that's the first integer. Then it is g of the quotient Riemann surface, the genus of that. And then they are all of the following form, p comma, actually, they're written in the opposite order. So q, y, p, q, y. So, sorry, y running in delta. Okay? So there's this here. So magically, this is an integer. It's an overall topological fact. That's, of course, the genus is an integer. And then there are these co-prime integers here. And because I've sort of put it in a special case where p is an odd prime or just prime, always get p here. Okay, else I could have gotten something that was divisible by, or something that is a divisor in p. Okay, but these are the Seifert invariants of this guy. And it turns out that there are a couple of exceptions where the Seifert invariants are not diffeomorphism invariants. So there are 4 special examples where these are not diffeomorphism invariants. The rest of the time, these Seifert invariants are actually diffeomorphism invariants of the 3-manifold. So Seifert-fibered manifolds, there's a special class of 3-manifolds that have a structure of a singular circle bundle over a orbifold. And the singularities in the circle fibration are over these orbifold points. And so they can be obtained by taking taking a circle bundle over the surface of Euler of degree B, and then doing surgery along the special fibers, according to the data, alpha I, beta I. And so for all possibilities of these invariants here, you have a Seifert-fibered manifold. And it turns out that whether it is a finite order mapping torus is equivalent to B being equal to this quantity here from these. Of course, in general, you would get, beta I over alpha I here. And so if that thing is equal to B, then it's actually a mapping torus of a finite order automorphism. Okay, so there are lots of these via what I just said. All right. So let me see. Yeah. So maybe let me try to make some motivation as to why do we want to study this. I mean, it's a nice thing to study, but let me just actually motivate this. And so what I want to do is I want to consider the motivation, and the motivation will be yeah. So let n be the moduli space of semi-stable, well, I mean, in this case, it's stable bundles of rank 2 and determinant isomorphic to, again, lambda. So just the bundle space. And then, of course, what I can do is I can sort of introduce L, which is just L restricted to n, like this. So that's the determinant line bundle now just over the moduli space of bundles. And in this case here, what happens is that HQ of n of this L to the k, this is 0 if q is bigger than 0. Then the higher cohomology groups vanish. And I can introduce another character that has no t in it, just chi k of f, to simply just be the trace of f's action acting on H0, L to the k. And of course, this is exactly the same if I summed over q because of what I just said, -1 to the q, and then trace of f's action on HQ of n L to the k. Right? Okay. And so actually, shortly after we had left Oxford, I met Oscar again. And he told me quite a lot about equivariant bonds. He had also told me about that while we were in Oxford. I never listened to him much about that. But now I all of a sudden started listening to him. And so maybe I'll write up a theorem that arose, therefore, from basically the basic ideas of somehow how to understand the action on n was through Oscar's ideas. But in the beginning, I'll formulate a theorem that looks quite far from this, but then I will gradually get into the part about fixed points. So the theorem is one that I proved in 1995. And so it says that this guy here, chi f, only depends on the Seifert invariants of XF. So it's completely parallel to the other one over there, right? But now it's only for bundles. And so let me try to explain a little bit about how this goes. So actually, what I really proved is the following: that one. I really proved that the following data only depends on this I ciphered of XF. So one, there is a finite subset of P1 up to N. Actually, this starts with 0. So there's a subset of this set here. And 2, for all C in this subset, there exists a polynomial, PC, which is with rational coefficients, but where I have adjoined the pth roots of unity. So mu p is the pth root of unity. So there exist these polynomials, and there exists dc, which is a positive integer, such that this chi of f, chi k of f, has this very nice form. So you sum over the c's in this set, then you take e to the 2 pi I k c over p, and then you do k to the dc times pc of 1 over k. So just a comment about why I write it like this. This is, of course, nothing but just k of the polynomial. But when you write it out like this, it turns out to be exactly what is actually, yeah. Sorry. So, yeah. So there is something called, I'll get into that in a second. There's something called the Witten-Resetiken-Terray quantum invariance of 3 manifolds. And that one is conjectured to be of a form that is similar to this for all 3 manifolds. It's namely a finite sum over Chern-Simons, classical SU2 Chern-Simons values of the 3 manifold. Then it is e to the 2 pi I k times that Chern-Simons value. Then it is k to the some integer times a Lorentz series in 1 over k that depends on C. So that's what's called Witten's asymptotic expansion conjecture. Now, in this case here, something weird happens, because normally what happens is that these series are divergent. But in this case here, they are all totally convergent. So there's no need for Borel resummation and so on. It's just completely convergent. And actually, the quantum invariant, which I'll show you in a second why I say this is the quantum invariant, this quantum invariant here is equal to its asymptotic expansion. So this formula, so a formula of this type here was kind of interesting, and it comes out of the geometry of the situation.
Yeah, formula there, I am a bit confused. You have H0 there.
Yeah.
You have HQ, but where those 0? I'm a bit confused.
Sorry, it's because I want to use Lefschetz-Riemann-Roch theorem. And so therefore, it really is equal to this, because all the higher cohomology equals to 0. But I just remarked that, of course, it's also equal to this, because all of the rest cancels. So I'm going to use the Lefschetz-Riemann-Roch theorem, of course, to analyze this. Okay, so I'm going to come back to this mystical statements about quantum invariance a little later. But now I want to try to, give you an idea about how can you prove something like this. Okay. So I'm going to introduce the following notation for, this is the fixed variety of this. So F is acting on this variety, and there is a fixed variety, right? So it may not be fixed points, which it generally isn't here. And so there is a fixed subvariety under the automorphism, and I'm going to denote it like this. And I'm going to, yeah, okay, fine. So, right. So what I want to do now is the following. So I'm going to write this guy as a union over C in C of union of components. And so now I want to tell you what this is subset here. And so this subset here is such that if I look at the trace of F's action on L restricted to this union of components that I've just called N/C, then the trace of this guy acting on the fibers of L is e to the 2 pi I C over P. So I take my line bundle and I restrict it to the fixed variety. Then the automorphism acts on the line bundle over that. So it's now over the identity that it acts. So therefore it must act with a root of unity of order P on that set. Now I collect all the components for which it acts exactly this way. And so this creates for me this subset inside here, namely the possible root of unities that I see when I vary over all the components. Okay, great. So now I'm going to say, let's look at the first Chern class of L and then pull it back to this NC. And I'm going to call that omega C. It turns so the first Chern class of L is really the omega, the symplectic form on the ambient space, right? And so these will be symplectic forms on these subvarieties. Okay. And so in that case, so when I now apply the Lefschetz-Riemann-Roch theorem in this setting here, what I will get the following. Namely, I will get that the entire character is equal to exactly this expression here, because I'm getting this here out from the restriction of the line bundle to the varieties. And now I want to give you a formula for what this PC of K is. So this PC of K, or set, I could have written of set, but it's the following. This is exp of K omega C cup. Then there's the Chern character, equivariant Chern character. I'm going to tell you what that is in a second, of lambda minus 1 of NC inverse. I'm going to give you what that is in a second. Coupled with the top class of this component. And then, of course, all of that evaluated on the fundamental class of this union of components. So I have just applied the Lefschetz-Riemann-Roch theorem to this Kähler manifold N with coefficients in the L to the K. And so I will get exactly this. Now, what is this? So this is, of course, some contribution from the normal bundle that I just want to try to describe for you very quickly. So I'm going to introduce, this is a different N than the curly N for the moduli space of bundles. I hope you can see the difference. So I take the tangent space to the whole variety and I restrict it to this union of components. Then I factor out the tangent space along the components. Then I take the dual. So this is the co-normal bundle. Okay, and so lambda minus 1 of this co-normal bundle simply just means you take the alternating sum of the wedge powers of this guy. And so this guy lives in equivariant K theory over set P of this component, right? So the normal bundle is acted upon by this automorphism, and the way that it works for finite automorphism is fantastic. There's no degeneracies. So the eigenvalues of it are all the roots of, possibly all the root of unities that are not one. So the one eigenvalue will be exactly along the fixed variety, and then you will have other roots of unities that are not one normally. So normally he meant normal to the right. So what I'm going to do is I'm simply just going to, I now look at the following, which is a localization operation, which goes from this equivariant K-theory of the fixed variety over to the absolute K-theory. In fact, this is algebraic in this case here, over the fixed variety, and then tensor set to the mu p. And so how do I get this map here? Well, if I have, it's easiest to say it on bundles. If I have a bundle here, then what I do is I decompose this into sub-bundles corresponding to the eigenvalues. And I just map that to the bundle, tensor the eigenvalue, sum over the eigenvalues. So that's this map L here. And now what I can do further is I can take a trace, which starts at the end of this one. Maybe I just write it here. So I could take a trace here where I just go into adjoining this mu p. So technically what it means is that you take this and you divide by the sum of all the p through the units is equal to 0. Okay, so you can trace and go here too. And so this guy, this whole guy here is, so lambda inverse of nc, it's actually equal to the trace of the localization of lambda minus 1 of nc. Okay, and so when I've written it like this is just the usual Chern character of this guy here. So I'm in K-theory, adjoined this root of unity now, over here after taking the trace. Now I just apply the Chern character. So, well, after inversion, right? So I invert this. So it turns out this element is exactly invertible inside that ring. Okay. So then I invert this guy, I take the Todd class, and then I get this. So you see that the way that you can now try to attempt to prove that these polynomials here only depends on the Seifert invariance is to somehow express this whole, first of all, you want to understand that the fixed variety only depends on the Seifert invariance. I'll tell you that in a second. Second of all, you have to show that this combination of cohomology classes can be written in terms of standard generators of the cohomology ring for this fixed variety here, only using the Seifert invariance. Then we're done. And so to do that last part, one needs, or at least I found it useful to use this Nielsen localization. So what I want to try to do is show you how to, for example, understand the first thing we started with. So somehow I think if I show you that I can understand this bundle here in terms of generators, maybe you can believe me that it can be done all the way through. So everything is sort of determined by this. So, this is Nielsen localization. And it's not the Nielsen of the Nielsen realization and the differential Nielsen coordinates. It's a different Nielsen. Okay, but Danish though. So I'm going to look at the projection of taking this union of fixed varieties. I'm crossing this with the curve, and then I'm looking at projecting onto a subvariety in the moduli space like this. And so I'm going to look at the universal bundle over this cross product, like this. And so the diagram that I want to consider is the following. So I can take equivariant K theory of this whole cross product here. So the automorphism acts by the identity here, but it acts on the Riemann surface, right? So I'm going to take this, and then I'm going to localize it a certain ring, and I'm going to tell you what this ring is in a second. But then here I have my localization function that I just described over there. And so that lands us in algebraic K theory of the fixed variety. What's the fixed variety? Well, nothing happens on this part now, but then I get the fixed variety of the curve, which is what I call delta. So remember, delta are the fixed points of f on C. I'm just localizing with respect to f acting on C. Now here I can push forward along the curve. And so if I push forward along the curve, you know, if I do the proper push forward in K theory, I'm going to get minus the cotangent bundle. Sorry, I'm going to get minus the tangent bundle, because it's H0 minus H1, and H1 is exactly the tangent bundle. Okay, so I end up in equivariant K theory of the fixed variety, tensor this ring lambda. I can localize further here, and I end up in algebraic K theory of the fixed set, localized at lambda. And here there's also push forward. And so this is a very simple push forward. This is a finite set. So I'm just pushing forward over that finite set, the fixed point. And so Nielsen localization says that this here commutes if lambda is the localization of, if I take this ring here, x to the p minus 1, so that's of course the same as set drawing the root 2 unities. But now I localize the following multiplicative set. It's 1 minus x to the I, where I is running from 1 up to p minus 1. So if you localize this set here, you get lambda. And basically what this is saying is that when you do this kind of localization process, you can remember everything about the K theory except for the augmentation, except for the ranks of the bundles, if you like, very simply said. But the ranks of the bundle I can control with index theory. So that's not a problem. So I get all the rest via this localization. And now what is the formula I end up with when I trace around? So I end up with that if I look at the localization of the tangent bundle to the whole variety localized, at this fixed variety, with the tangent bundle to n restricted to the sub-variety, then this is in K theory the same as minus sum over y in delta, and then the localization of the universal bundle fiber over y running through these points, and then tensor with lambda minus 1 of the cotangent bundle at y of the curve inverse. So here I'm just repeating localization, except I'm not now localizing on the moduli space. I'm actually localizing on the curve in families. And so this guy, he is very simple to compute. He just becomes, you know, we know exactly how you act on the tangent bundle, right? This is given by these Seifert invariants that I wrote before. So actually I can write down explicitly what this element here is. It's namely 1 minus x to the q y twiddle to the minus 1. So you see here we need the inversion of these, right? All right. So now I have a very nifty expression for the tangent bundle. It is simply this object here. Just the fibers of the universal bundle over these fixed points, and then there's this correction factor. And now I can just make all the algebraic operations, take the sub-bundle, divide it out, and so on. And then I can actually compute this element here explicitly in terms of, well, what? In terms of E slanted with points. So that's part of the standard generators of the cohomology ring. right? And the same thing goes with the Todd class. This is kind of standard stuff, but actually of which variety? Of which variety? Because somehow right now I'm speaking as if we know what the fixed variety is. And the thing is, we do. So let me write up what those fixed varieties are. So what are these fixed varieties? Well, now I'm going to introduce a little bit of data, and then I'm going to write down what these fixed varieties is. So I'm going to introduce gamma. So this is going to be all the maps gamma from the fixed points, which assigns to each of the fixed points an integer between 0 and p minus 1/2. Okay. And then I'm going to use this notation here, sub p for the map that goes from set to 0, 1 up to p minus 1. Okay, now I'm going to introduce delta gamma. So for any element of this here, I'm going to look at the y's in delta such that gamma of y is different from 0. Okay, and now I'm also going to introduce d gamma, some divisor, and this is the y's in delta gamma, which I just defined, such that if you look at minus qy, so it gets a little bit technical, but just bear with me for a second. I introduce all these spaces here. So these two divisors here. Now I introduce lambda gamma. This is going to be a line bundle downstairs. It's the line bundle I started with of odd degree lambda prime tensor, and then O of d gamma, which is this divisor here. This is qy gamma of y. The pth part is bigger than p minus 1/2. And then I introduce the following weights: omega gamma from delta gamma to q squared. And the first weight is 0, and the second weight is this guy here, minus 2 qy gamma of y, and then divided by p. And then the point is that, and this is where I really benefited from the discussion with Oscar. And so I did this together with my former student, Jakob Grove. And some of you may know the geometry Grove better, but that's his what is it called? Brother-in-law, I think it is, something like this. What it says is the following, that there is, so I have a phi from the fixed variety of n over to, here I have a union over gamma in gamma, and then I have n cf comma gamma. So this is the moduli space of parabolic bundles of CF, where the structures are concentrated at delta gamma, and the weights are given explicitly here. And so what is going on here? And so what's going on here is that you have an automorphism on the Riemann surface. You know that you abstractly have a bundle that is invariant under F up to isomorphism. Then Oscar told me that it's actually possible in this case here to lift the automorphism in such a way that you get an action of set P on the bundle total space that covers the base. It's a really nice little neat argument. And so now what you do, you take that, you look at the fixed points. In the fixed points, it will act by, since it's finite order, it will act diagonally with two eigenvalues. What you can do by tensoring with a line bundle is to make So drift both of the eigenvalues in such a way that one of them is the identity, the other one is something else. And then you do Hecke transformations appropriate number of times in that other direction, in that flag. And then you end up with a parabolic bundle that has encoded the way that the action is. So eventually you end up with something where it acts by the identity on all the fibers over the fixed points, and then you can descend the bundle. It's a pullback from the base, but it's a parabolic bundle to remember the whole structure. And so that's the reason why this works, basically. Okay. So, and therefore you see the fixed varieties are actually nothing but moduli spaces of parabolic bundles. And therefore, these are exactly the known generators of the cohomology ring of those moduli spaces. Okay, so yep. So I think that I want to, I have to make a choice now. So I will definitely make sure I talked about the Higgs bundle case. So if you want to ask me a question in the question session, please ask me, how is this related to quantum invariant? But so let's see what happens now in the case of Higgs bundles. And so the nice thing is that there is the following theorem of Oscar's. And Wilkins. And it says that, so I had a little, I didn't give it a name, little phi. So now we have capital phi. So if I now look at the Higgs bundle moduli space, and I use the same notation, so the F fixed point set of the Higgs bundle moduli space is isomorphic to a Higgs bundle moduli space, or parabolic Higgs bundle moduli space, where the weights are exactly like over there, and the residue of the Higgs field is 0. So this is actually a T equivariant phi. It's equivariant with respect to the C star action on both of them. So that's basically what we need in order to try to lift this to the Higgs bundle moduli spaces, except the Higgs bundle moduli space is not projective, right? I mean, it's non-compact. And so we need another theorem to deal with the non-compactness. And of course, we have to utilize the C star action. And so the theorem is the following. So this is a theorem due to Wu. And I'm going to abuse this theorem grossly. I'm just going to state it in the Higgs bundle case. But it applies to the Higgs bundles. And so it says the following. So we have, of course, like this. So we can, Okay, so let me just write it out like this to begin with. So the fixed point set will have, of the C star action, will have some components. So Nigel worked out exactly what these components are. So I'll get to that in a second. But we know exactly what these components are. And then we're going to take the normal bundle with respect to those components. So I should have written like this. So maybe I write it in order to be consistent with previous notation. I write it like this. So these are just the normal bundle to these fixed varieties. Everything is smooth here, so everything is hunky-tonk. And then I'm going to write a plus or minus up here, plus or minus here. So some of them will have positive eigenvalues, some of them will have negative eigenvalues with respect to the C star action, right? So positive characters, negative characters. Okay, and then I'm going to introduce nu m, which is the rank of the normal bundle in the plus direction with the convention that I'm using. And then this theorem of Wu says that in the C star equivariant K-theory of a point, so in other words, just in terms of C star representations, if, maybe I have to write it up here. So it says the following, that suppose you sum over m equals 0 to infinity, you sum over q, and you take -1 to the q, and then you take HQm of the Higgs bundle moduli space L to the k, T to the m. So this guy here is, so there's some very technical things about the C-star action that makes this theorem actually click in this case here. But so it says that this here is the same summing m equals 0 to infinity, summing q, and then summing O. So yeah, there are going to be twiddles on this m here, not to confuse it with the m before, right? So this m here is an integer, but this m twiddle here is a component. And so I get -1 to the q plus nu m. And then I get the following cohomology group, HQ, and then so I'm just going to write it like this, because then that incorporates all the weight spaces in one go. So I take m twiddle, and then I take ST of the negative normal bundle, tensor ST of the positive normal bundle, tensor the determinant of the positive normal bundle, tensor L to the K. And then that's it. Take the m's, so there's a twiddle, forgot here and here, take the m's part of this and multiply by t to the m. So taking the m's part here doesn't do anything on this variety and the cohomology, of course. All it does is just break this bundle here into isotypical components. And so it's just, this is an infinite rank bundle, but taking the m's isotypical component just takes a finite rank bundle out of this. So that's the localization theorem of Wu. And this is fantastic. This is also natural, so that it's F equivariant. And you see all of these guys here, well, part of the assumptions of this whole theorem is that this space here is projective. This is compact. And so now I can run what I was doing before, just take and run the Lefschetz-Riemann-Roch theorem on this compact variety. So of course, it will split over the components, and I will compute what the fixed varieties are on the components, and then I will take the trace on all these pieces here. They're finite rank bundles over, because they are the m isotypical component here, just run the same program. And now the idea is that you use Nielsen localization also to rewrite everything in terms of natural generators again. Because you have the same kind of, by Oscar's theorem here, you have a moduli space of parabolic Higgs bundles to be had there. So, yeah, I mean, I think I kept track, so I've spent 53 minutes, so I'm actually out of time. But of course, you all know what Nigel's description of these fixed points are, so no need to repeat them. And, it's very simple. I would just get this bundle here, localized to the varieties and so on. So I don't want to write this up. So I'll stop there. Thank you.
Thanks a lot. Any questions? Yeah.
Thank you for your talk, and let me apologize first because I'm not going to ask you how is this related to quantum invariance. Instead, I am going to ask you if you had a subgroup of the automorphism group, not necessarily cyclic with P prime.
Yeah.
The equivariant Hitchin index makes sense to define.
Yeah.
And also that theorem there is actually true also in that situation. I don't know about the cipher thing. I don't know what you get. Is there a statement there?
Well, so you were asking about a case where I don't take a single element.
But you take a subgroup which is necessarily finite,
Right.
because the group
You
of
take a
elements-
finite subgroup And so the thing is that will correspond to a whole stack of different 3-manifolds, because each element in this group will give you a 3-manifold. So it will be a stack of 3 manifolds that you're treating in one go. And it's totally possible to run the whole thing. Now you will have a non-abelian localization instead, because this finite group is non-abelian. But the whole thing works in this setting as well. So you could do this. And then you would localize further to the fixed points of that action, which is smaller. So that's totally doable. So
Thank you.
there's nothing in the technology that doesn't work in that case. Yeah.
Any other questions?
Yeah, I have one. So what about
quantum invariants?
Yeah, how about quantum invariant? Thank you for the question.
Yes, so if you can tell us about in 1 or 2 minutes.
So I will deal with that in 1 or 2 minutes. And maybe I will spare you the formula then. But the thing is that there is an absolutely explicit, so I should say the following. Yeah, so there is a theorem that there exists a map mu from the positive integers to mu p, such that if you take the Resitigan, so the Witten Resitigan-Tureev invariant at level k of xf, then that is equal to this mu of k. So it's just kind of some pth root of unity that you actually, this is not quite right. It's not like that. It is a k plus second root of unity. So it's level dependent, but it's completely under control. I mean, one can write it down explicitly. This times the character of f. So this is a theorem we now know. Okay, this was not known when I did my work in '95. And so this follows from a whole sequence of sort of, stringing things together. First one starts with Nigel's paper that he constructed his projectively flat connection. Then you refer to Laszlo, that proved that that bundle, the bundle of H zeros of L to the K of the moduli space of bundles over Teichmuller space supports a projectively flat connection. Then you refer to Laszlo's theorem that says that that bundle with its projectively flat Hitchin connection is isomorphic to the space of the vector bundle of conformal blocks and the TUY connection to Shio, Ueno, Yamada. And then you can refer to work of Kenji and I, where we proved that that representation you get of the mapping class group there is isomorphic to the one that comes from Resitigan and Tureev projectively, from their combinatorial construction of the whole T of T. We prove, in fact, more. We prove that the two give modular functors and that those two modular functors are isomorphic. So the whole T of T's are determined by, a system of representations over all surfaces with some degenerations. And so therefore, a corollary of that is actually that these two are equal up to this here. And I can write down explicitly what this is. And so now that actually opens a possibility, namely that I expressed this character chi as a combination of characteristic classes over these parabolic moduli spaces. But this side here is absolutely absurdly explicit. This is a finite sum of j equals 1 up to k plus 1 of some expression involving signs, sign of something, and then there's some exponentials. And so that means that we can actually have explicit formulae for all these evaluations of cohomology classes on these parabolic moduli spaces. And so question to the whole audience is the cohomology ring known for all the parabolic moduli spaces? In the sense that one knows how to pair all the generators of the cohomology together against the fundamental class. Because if you do, you can check this. But if it doesn't, you can use this formula here to get information about the cohomology ring of the moduli space. That's point A. Point B is that the situation for our work with Thomas and William for the Higgs bundle moduli space is very similar to what it was in '95 when I did my work. Namely, in this case of the Higgs bundle moduli space, we do not know how this relates to complex quantum Chern-Simons theory. We don't have a proof. We have an expectation. And physicists have an expectation formula for what this is supposed to be. again, totally explicit. It's a T deformation of this and T matrices that go into this. And so that would give similar sort of expectations for what are the pairings of all the equivariant classes, T equivariant classes on the Higgs bundle parabolic moduli spaces. With these cases where there's zero residue. And so there's the same question goes to the audience. Are those cohomology rings known? If not, one can use, there's a huge opportunity in using this and proving those obvious conjectures that comes from this. Thanks for the question.
The curve CF doesn't have genus bigger than or equal to 2, right? The curve CF.
No, it could be have zero.
Elliptic or P1, right?
Oh yeah.
So doesn't that probably mean that the answer to your question is probably no, at least in those cases?
Yeah, I think so too, right? Yeah. But it's just I would like to hear. I mean, there are experts in the room about. No.
One just tiny remark is. One tiny remark there is that for parabolic bundles, you have Kerwin surjectivity. So you have I think you have Kerwin surjectivity for parabolic bundles. So I think you have a set of generators at least, and like that. For SL2 Higgs bundles, you don't have Kerwin surjectivity.
Yeah. So the question is, does these generate? But at least you get information about these, basic similar generators that you get in the Higgs bundle. So that's further question. Do we actually get all of them? And in this case, it's also an interesting question. I mean, do you actually get from these formulae all the pairings that you need to determine the cohomology ring? But I think these are completely unexplored questions, but there are lots of explicit formulae. So you just apply Don Zagier to this side here. You get the coefficients on that side, right?
Of course, the conjugacy classes you get here are very special, because they are finite elements, right? So it's parabolic moduli space of parabolic bundles, but with a rather.
That's right, but
so
I mean, there is this
easier maybe to compute.
But there is this chamber structure, right? And I mean, maybe there's some within the chambers, there is some deformation and variance, and so I assume that there's some local constantness of this, and then there's some jumping phenomena across walls and so on. So, yeah, that's right. But you could possibly get quite a lot more than just those particular weights this way.
Any other questions for the speaker or for the audience? If not, let's thanks Jørgen.